So it's a pleasure to have Zohar and Simeon prepare us for the 40-minute discussion on flux tubes and effective field theories.
All right, thanks so much. I've enjoyed the talks this morning tremendously. Well, actually, I'm not quite going to review the confining flux tube. I prepared a few slides emphasizing some interesting aspects of deconfined flux tubes. And Gabriel on Monday will probably give more details of many things I'm going to say very quickly here. So it's more, so we usually emphasize the difference between area law Wilson lines and perimeter law Wilson lines. And we usually say that a perimeter law Wilson line is screened. So one thing that I wanted to just maybe provoke a little bit or explain in the slides is that this distinction is way too crude. And I'm going to tell you some very basic facts about Wilson lines in conformal gauge theories or conformal field theories, where obviously all the line operators, including Wilson lines, have perimeter law, but that doesn't mean that they're screened. So I'm going to maybe try to make a more refined distinction between truly screened operators and not quite so screened operators. So this is the setup. We have a conformal field theory in D space-time dimensions and a one-dimensional defect. This one-dimensional defect could be a Wilson line. It could be a line operator, even in some ON type Wilson-Fisher fixed point. There are many, many examples. And actually, most of the work that we've been doing recently with Avia, Raviv Moshe, and Mark Mezé, and Gabriel, that Gabriel will summarize, is about magnets, various line operators in magnets. But anyway, from the condensed matter point of view, what is this physical system that we're talking about? We're talking about a spin chain that is tuned to a critical point, and we have some dirt / doping / impurity, just because if we take a time slice of this setup, the one-dimensional defect is a point in space. So the physics is that we have some kind of garbage, impurity, doping. There are lots of constructions of line operators in various field theories. Not going to go over it. It's just a list of various constructions that some of you are familiar with from the literature in condensed matter and high energy physics. Obviously, this problem is very interesting in condensed matter, so there is huge literature on line operators.
Zohar, I'm sorry.
Maybe we can discuss in the 40 minutes because I barely have like. Okay. Yeah, we have 40 minutes. I'll be more than happy to.
No, it's not discussion. I'm just trying to understand when you're saying one dimension, you mean in time or one dimension in space? I mean, does it?
One dimension is in space time. So if you take a time slice, it will be a point. So
yeah, it's what I'm checking. I'm sorry.
Yes. So a conformal impurity or a conformal line defect would preserve an SL2R symmetry times transverse rotations. But in condensed matter, or in this general setup that we have line defects in conformal field theory, the line doesn't have to preserve SL2. It may just preserve translations along the line. So the terminology is that we have critical impurity, critical bulk, but the impurity may be critical or non-critical. It may be that there is an RG flow on this impurity or the line defect. So one important observable that tracks this RG flow on the line operator is what we call defect entropy. It's a certain differential operator. R is the size of this loop. So we take the line operator to be a circle. R is the radius. We act with this differential operator on the expectation value of the circle, and we call it defect entropy. It's just a name that I can explain the reason for this name in the discussion. When you take the circle to be very small, it will be like some ultraviolet fixed point of the impurity. When you take the circle to be very large, then this defect entropy would approach some infrared value of this impurity. So there is an RG flow on the line operator. It's a very standard situation, QFT. We have some RG flow. Here, the RG flow is confined to the line. I mean, confined in the heuristic sense. It's limited to the line, and the bulk is conformal. Now, there is a gradient formula for this renormalization group flow, which is maybe a little surprising. It's a very general gradient formula, which says that the defect entropy actually monotonically decreases as you increase the radius of the loop. And this leads to many constraints on the possible infrared phases of impurities in condensed matter and high energy physics. Gabriel will probably give some examples. But let me now get back to the discussion of what the confinement or screening means. So even in four-dimensional conformal gauge theories with fundamental matter, such as Seiberg-Witten theory with four hypers, you might think that the fundamental Wilson line is a stupid observable because there are fundamental quarks in the Lagrangian. So why are we talking about the fundamental Wilson line? It's obviously screened. But actually, this fundamental Wilson line has a non-trivial conformal fixed point as a line operator. So this line operator does not flow to a trivial line. It flows to a non-trivial defect conformal field theory with SL2 symmetry. So it's not screened in this sense, even though there are fundamental quarks in the Lagrangian. Similarly, the adjoint Wilson line in n equals 4 super Young-Mills theory is not screened either, even though there are dynamical gluons. So screening should really be interpreted in the most refined sense as having a line operator, which is a trivial unit operator. But even line operators that you might think are screened in the textbook sense, that there are fundamental quarks in the action or whatever, they might not be actually screened. They might furnish a highly non-trivial defect conformal field theory. So let me now give you some examples of line operators in condensed matter or in magnets. I'll give you two examples. I'll talk about screening for 2 minutes, and that's it. So one very general class of line operators are exponentials of bulk operators integrated on a line. So from the point of view of renormalization group flows on impurities or line defects, the ultraviolet is the trivial unit operator line defect, but the infrared could be highly non-trivial since you take a bulk operator and integrate it on a world line, on this one-dimensional object. So for instance, this describes the infrared of taking a critical magnet and putting magnetic field at a point on a lattice site. It's a very rich subject, and actually that's what we wrote recently a paper about. There is also Monte Carlo simulations, and there will be more experiments in the future about the reaction, like quantum antiferromagnets with a pinned magnetic field. We actually solved this model exactly in the large N limit. Gabriel will probably explain these formulas, but these are the defect entropies, the scaling dimensions, and so on. So this is a line operator in just a magnet. There are even more interesting line operators, let's say in the O3 model, which don't involve turning on background external fields. So here you start from some quantum mechanics on the line, which is a spin S representation of SU2. You couple it to the bulk, and you get something that looks a lot like a formula from Wilson line, a formula of Wilson lines. But here there is no gauge field. It's a past-ordered exponential of Wilson-Fisher fields, and the trace is taken in some spin S representation of the SO3 symmetry of Wilson-Fisher. It's a very interesting problem to solve this line operator. What is the infrared? What are the scaling exponents? And it's actually realized in the lab pretty easily. It again corresponds to putting some dirt of spin S in a quantum ferromagnet. No background fields in this case. It's even difficult if the bulk is free. Here I just emphasize that even if the bulk is not the critical O3 model, but the free O3 model, it would have still been a difficult trace to compute because it corresponds to a more or less some sort of problem of random magnetic field in NMR, and it's not exactly solvable. So the big problem is it actually screened for some values of S? Obviously, there are particles in the bulk of spin S equals 1, but it doesn't mean that it's screened for generic values of S. And it's an important problem about the phases of various impurities in condensed matter. So these were just a few comments about what the confinement actually might mean or screening might mean. And now I'll let Simeon make his comments. Thank you.
Thank you very much. And let's pass it over to Simeon.
Oh, hold on. Let's see, share screen. Where is it?
So Zohar used 9 minutes. So you have 11.
Oh, I got a lot. Awesome. Okay. Is it showing up? Sorry. Where is it? I'm going to share screen again. Share screen. Can you see it?
Yeah.
Okay. Full screen. Okay, so thank you. So the string theory of QCD was originally formulated to explain remarkable robust patterns in hadronic spectral data, as you know. All hadronic states appear to be arranged in a tower of resonances that can be plotted on a graph of mass squared versus angular momentum as straight lines with a common universal slope, more or less. So yeah, Regis slope is alpha prime. So for open strings, the mass squared is J over alpha prime. Classically, alpha prime is 1 over 2 pi inverse string tension. So we know today, of course, that the string theory of QCD is not really a complete description at distances much shorter than or comparable to root alpha prime. But we can still treat string theory as a perfectly good effective theory on scales longer than that. And that's good because many interesting things happen on those scales. So for a string with large angular momentum in particular, the length goes as root J alpha prime. So we should be able to use the effective theory of the string world sheet when J is much greater than 1. In fact, doesn't even have to be much greater. One of the important points about Ratchet theory is that it extrapolates, very well down to low values of angular momentum. In fact, in some sense, continues in a controlled way into the negative spin regime. So anyway, this point of view allows the computation of corrections to the Regis spectrum of the form mass squared equals J over alpha prime with corrections of relative size and powers of negative powers of the angular momentum, and I'll get to what those powers are in a moment. Depends a little bit on the situation. So when the string is large, the short distance structure is irrelevant in the technical sense of the renormalization group. The dynamics should be described by the most relevant terms one can possibly write in a local action for a string, invariant under all the appropriate symmetries. The most relevant term invariant under the Poincare symmetry is the Nambu-Goto action, which is just the area of the world sheet times the string tension. So the Nambu-Goto action describes the spectrum with arbitrarily good precision when the string is large, with typical scale much greater than root alpha prime. So the Nambu-Goto action describes the leading contribution to any observable in the limit r much greater than root alpha prime. Less relevant terms in the action contribute with negative powers of root alpha prime. And as an operator scaling his length to the p contributes to any observable at relative order r to the minus p plus 2. And so this kind of analysis of large R corrections is easy. Just classify possible invariant operators up to some order in the inverse length. Then every observable can be computed in an expansion in R over root alpha prime, modulo unknown Wilson coefficients of those operators in the action. There are a couple of subtleties to it, however. So first, a quantization of the string. Early work used static gauge due to Lusher and others. It's a difficult gauge to work in. It's hard to keep track of covariance. More recently, quantization in covariant gauges was done, starting with Polchinski and Strominger in the 90s. More recently, there's been work sort of covariantizing further. And one important development was that the matching of quantities, the confirmation that effective string theory in arbitrary d dimensions gives the same results regardless of which of these formalisms you use, as you would expect. But it took quite a long time and a lot of work to confirm that, and some heroic people at mostly Weizmann and NYU did all that. So, but in the modern covariant formalism, somehow the easiest to use once one knows its equivalent to everything else, it's just the same as the Polyakov formalism, but with an anomaly term to cancel the conformal anomaly. As you might expect, this anomaly term is proportional to d minus 26, so it vanishes in the critical dimension, but the theory can be quantized in any dimension. And again, it matches quantizations in other formalisms, including static gauge. But in whatever formalism, you can compute lots of stuff. For straight static strings wound around a compact direction, you can compute the spectrum, which has a sort of simple semi-classical form up to 2-loop order. Then at 3-loop order, there's an interesting universal coefficient, universal term contributed by the anomaly term at 3 loops. And then there are some non-universal terms depending on adjustable Wilson coefficients at the next order after that. We can also consider rotating closed strings, say with non-zero angular momenta in 2 planes simultaneously. And again, you get the same sort of thing. You get the sort of classical mass squared from the classical rotating string. You get a Casimir term proportional to the number of transverse oscillators, d minus 2, and then you get this contribution of the anomaly term proportional to d minus 26. And you can see that this becomes singular when one of the 2 angular momenta is turned off, and I'll mention that at the end. Another subtlety is that when the string is open rather than closed, there are singularities at the boundary that modify the organization of operators at the endpoint and modify the power laws that appear. So the singularities don't make the whole EFT breakdown. You still don't see the UV degrees of freedom, but the organization of the derivative expansion changes. So for Dirichlet boundary conditions, the world sheet ending on a Wilson line or heavy particle, instead of just even powers of L, there are odd powers of L that enter as well. This was first studied, I believe, by Komargodski and Aharoni. For strings with Poincare invariant boundary conditions, Neumann boundaries, free endpoints, the organization of operators changes again, and there are half-integer powers of L that show up in the expansion, leading to a large spin expansion in quarter-integer powers of J. So in the Polyakov formalism, this can be understood because bulk operators are dressed with powers of partial x, which scales as J, but boundary operators are dressed with this funny invariant. It's the only invariant at this order. It's the largest invariant at the boundary at large spin, and it scales as J to the 1/4. And so again, you can quantize the open string. You get the classical energy from the Nimbus-Goto action. You get a Casimir term, and then you get this weird-looking function of the 2 angular momenta proportional to d minus 26 coming from the anomaly term. And then you also have an adjustable constant, an unknown Wilson coefficient, times this particular combination of angular momenta, and this Wilson coefficient corresponds to a sort of renormalized mass, highly renormalized mass of a quark at the endpoint, if you like. I mean, there are millions of things that contribute to it. It doesn't canonically correspond to a quark mass in any sense, but quark mass contributes to it. So here are some open questions. So you noticed that I said that the closed string energy is singular when one of the 2 angular momenta goes to 0. The effective theory on the singularity of the closed string, it's a fold singularity, the closed string is folded. This effective theory isn't worked out, and it's been one of the most challenging, I think. It's somehow analogous to the effective operators at the boundary of the open string, but it's more complicated because the fold can move. The fold can wiggle, unlike the boundary. So the effective theory at that fold is considerably more complicated. So we don't even really know yet what exponents, like the analogs of j to the 1/4, what exponents appear are contributed by the fold singularity. How many different Wilson coefficients are there at the fold? Is there a unique dressing rule at the fold? Dressing rule meaning, what's the field that appears in denominators, which distinguishes the open and closed cases, for instance. So empirically, for open strings, this is on the wrong side. Okay, so a second question: how does chiral symmetry constrain the effective terms at the endpoints, given that chiral symmetry is spontaneously broken in the vacuum? It's sort of, because chiral symmetry is spontaneously broken, it may be a little bit too naive to say that the j to the 1/4 coefficient should just vanish. But empirically, the j to the 1/4 coefficient vanishing actually is quite a reasonably good approximation, it seems, for meson trajectories involving light quarks only, such as the rho trajectory. The j to the 1/4 term is fit with data to 0 to a very good approximation. So is there any sense in which chiral symmetry forces that coefficient to be small or 0? Another question: are there ever logs? So to the order that's been computed for rotating strings, there have only been power laws of j and no logs of j, but logs are very interesting and important. So if so, at what orders do they appear and for what quantities? And then one other thing which would be very nice would be to check the predictions for subleading corrections against other descriptions of confining strings in the planar limit, such as via the S-matrix bootstrap. So as was done to leading order in work by Komargodski, Zhiboidov, and Sever, and for subleading order, in particular the j to the 1/4 correction was derived by Zhiboidov and Sever in subsequent work. But for instance, the universal term at j to the 0, the theory independent term at order j to the 0, hasn't been derived from S-matrix bootstrap or anything like that. So it would be really interesting to try to do that. So I think I'm out of time, so I'll just kick off the discussion with those observations and questions.
Oh, thank you very much. No, overall, you are more or less on time. Thank you. Okay, so let's open up to a general discussion about either the topics we heard or connections to the morning talks as well. So Igor.
Hi. Yeah, very interesting introductions. Just a very basic question. When you talk about so we heard about d = 3 and d = 4 effective strings and confining gauge theories. What are the models we have available for d above 4, like say d = 5? What would be the UV complete description of such effective strings?
Yeah, well, that's an interesting question. I mean, one thing I could say about that is that one thing obviously would be string theory, but
but we're talking about effective, like some kind of gauge theory or non-gauge theory, say antisymmetric tensor or
right. So for instance,
strings, or what are the things on the market?
Yeah, well, one thing you can do, which I didn't mention, but it's another important open question, is to do an effective analysis of strings coupling to light fields in the bulk. So you don't have to have just only strings and nothing else. So you could, for instance, have strings coupled to massless fields, and then in that case, there's a very interesting analysis one could do of the 2-0 theory on the tensor branch, for instance. And you know, there was some little bit of that was done in an old paper by a Modal, Ganor, and I forget some other people, but a sort of leading order effective analysis of 2-0 theory strings and on the in the spontaneously broken phase. But it would be interesting to go further and compute compute universal terms in the expansion and things like that, and compare those with other methods like bootstrap or whatnot.
Thanks.
Before I pass to Alexei, let me just tell people that if you have any comment that is related to what's being discussed right now, wave your hand and we will jump directly to the person so that we keep a...
How do you wave your hand?
No, you do like this. You just you turn on your camera and you literally wave your hand, and then I'll see you. And so, Kavli, I assume you have something to say about this endpoint. So
yes.
Go on.
I would like to make some comments about the talk of Simeon. First of all, I want to talk about this logic of starting with the long strings and expanding in powers of 1/L or negative powers of L on J. This is very nice theoretically, but it has very little to do with real hadrons. Hadrons of large spin or large length are all have very wide widths and they do not exist. So it's a nice theoretical exercise, but it's not very useful for understanding hadron physics. Secondly, I would like to ask about, to comment about the point that Simeon was making about the folding points and about this renormalization process. I think that there is a very useful tool to handle these issues, both open and closed, by adding massive endpoints. And for the closed string, you just add masses as regulators on the folding closed string. But in open strings, it's really physically the masses of the quarks endpoints of the string. Now, with this massive endpoints, there are no folds, there are no curvature singularities, and the endpoints and the folds and sinks are much easier, in fact, to handle. So I think this is not very well appreciated, but I think that the string of hadrons should be taken not as a string, ordinary open or closed strings, but rather open string with massive endpoints, with charges and spins and whatever you want to dress these endpoints. But that's, I believe, the right approach to the string theory of hadrons. Thank you.
Maybe I can ask something that is probably related. So what is the status of indeed the program of studying these endpoints with masses from the bootstrap point of view? Zohar, you had this paper with Amit and Sasha, and then they wrote the first correction. And is this something systematic that one could carry on this program?
It's a good question. Well, in the Polchinski-Strominger formalism, you have to understand how to render these massive endpoints into a conformal boundary condition. I believe it's a well-defined problem, but I have not seen much progress on it. It's perhaps.
Well, I mean, there's an operator you can just write down which adjusts the quark mass.
Yes.
I mean, in the EFT framework, I think it's kind of straightforward, but.
Yeah, in the EFT approach, it should be doable indeed.
But I mean, in Bootstrap, what's the obstruction to going to the next order? What it seems like people found it difficult, but I don't have a sense of why people found it difficult.
I mean, even leading order, Zohar, Sasha, and Amit have to be very smart to do it. It's hard, right? This problem. It's not like it's.
Yeah, but you know, usually with expansions like that, like the leading order is conceptually difficult, but calculationally easy, and subleading orders should be less conceptually difficult, even if they're more more complicated calculationally, right? I mean, usually once a perturbation theory is set up, you don't need like extra cleverness at every order, right?
My vague impression is that the main obstacle was that you have to understand how to quantize this theory with the massive endpoints, which I believe.
But why in Bootstrap? Why do you need to do that?
Oh no, I was talking about the ab initio approach to the effective field theory predictions.
Oh no, yeah, that's straightforward. We know how to do that. But
yes,
but in Bootstrap, why is it hard to calculate like the j to the 0 term, for instance? I thought that's what Pedro was asking.
Yeah.
But I think for leading term, correct me if I'm wrong, Zohar, but for leading term, you could argue very generically that there is some universality. Already for the subleading term, they benefited from having some explicit models to check.
Yes, I think calling this
to have things under control. So it becomes a little bit. It's not already 100% bootstrap. It's already a little bit.
I think calling this approach bootstrap is probably not the right word, because it's not an approach that has completely clear errors. You start from some leading order understanding of where the zeros or poles of the scattering amplitude might be, but then quickly you have to discuss some corrections to that. And I don't believe it's completely systematic like the bootstrap program.
So I guess the way would be to construct an amplitude where the intermediate states would have these endpoints, right? And then check that it goes through the bootstrap and so on, and use that check as inspiration to try to see what else could have happened there.
Yeah, I don't think that this approach is completely systematic. I guess Simeon means the approach where you take large S and large T, and you try to think about the amplitude as the sum over many positive terms that quickly grows. I don't know if in that approach the errors are completely under control. So.
May I have a question to Zohar?
But wait, let me go in order. Let me first pass it to Alexei, if that's okay.
Okay.
Unless it's exactly about this topic, let's go in order. Let's go to Alexei first.
Okay. Hi everyone. I also really enjoyed these talks. I have a question for Zohar. Suppose a line operator goes from being trivially to non-trivially deconfined according to the refined criterion that you told us about. Does that have some implication for the bulk phase diagram of that quantum field theory?
Oh, that's a good question.
Is it an order parameter? Is it an order parameter? That's what I'm asking.
This question is too difficult to answer. I can tell you that there is a conjecture in the literature, or a conjecture that I can formulate based on examples, which is that in gauge theories, Wilson lines never seem to have negative defect entropy. However, in magnets, for some reason, we found many examples with negative defect entropy, even exponentially large negative defect entropy. Whether this is a deep fact or a coincidence, I do not know. But I think it's a valid conjecture that Wilson lines always have positive defect entropy. I am not aware of a counterexample. So it could be that there's something fundamental about that. Maybe Gabriel has something to say, but this is a fact of life that so far there is never been an example with a negative defect entropy Wilson line.
And it cannot be zero either. That's the point.
Yes, you could formulate a conjecture that in every conformal gauge theory, Wilson lines in every representation would have strictly positive defect entropy. And if I'm not mistaken, there is no counterexample to this conjecture.
Mm-hmm. Mm-hmm. And is nothing known about what happens if the value of this defect entropy changes in some way that isn't analytic? Would that indicate some phase transition, or can that ever happen?
Changes under what?
And you vary some parameter in the quantum field theory, and this defect entropy changes.
So the bulk, you mean?
Yeah, in the bulk. Is that phase transition in the bulk?
Oh, I was always imagining that the bulk is fixed. If
But-
you like,
okay.
all the discussion was for a fixed bulk and the space of possible line operators in that bulk.
Yeah.
Now, if you change the bulk, well, I have no idea what's going on. I only know what happens when you try to flow between different line operators in the same bulk.
I see. Okay. Okay, good. Yeah, I'm just trying to see if this is a new order parameter for bulk phase transitions, but maybe it's not obvious.
I think there is something fundamentally different about Wilson lines that I cannot wrap my head around. That they do obey this property that I said. So
I see. Thank you.
Lance?
Hey, thanks for these introductions and questions sort of for Simeon and sort of for any lattice gauge theorists who might be out there in the audience, which was, I mean, Simeon, you discussed somewhat the open string spectrum, and there's some lattice data about closed strings and glue balls, and I was just thinking, I sort of mentioned this earlier in the program, maybe it would be interesting to have lattice simulations of theories where you put in fundamental scalars to try to mimic open strings at large N. And I'm wondering if you could measure some of these coefficients that way. And how feasible is that from the lattice gauge theory point of view, if people wanted to discuss that?
It's a very Lorentzian thing, right? Either scattering in the Regge regime or just directly looking at the spectrum of spinning strings. I don't know. I mean, I'm sure Kobe knows better than I would. What's the state of the art on lattice simulations of confining string, like the highly spinning part of the spectrum?
I mean, there's simulations we saw in a week or two ago in for closed strings for glue balls, which seem to have a pretty good match to a model for the closed string spectrum.
In 3 dimensions.
I think also somewhat in 4 too, isn't it? Or maybe it's only 3.
Oh, it's both 3 and.
I think there's 4 evidence in 4 dimensions as well. Yeah. So, and then there's the statement that the closed string spectrum is roughly the square of the open string spectrum, and the question is whether the lattice can see directly the open string spectrum by putting in some sources. You know, like massless scalars, since they're easier than fermions. And I'd wonder if they could do some measurements of some of these, you know, operators in the effective open string. It's not a real measurement because it's sort of an extrapolation to smaller j of something that's formally only valid for large j, I think.
I think this is feasible. I think this can be done. I mean, it can also be done, I mean, using, fermion sources. I mean,
wouldn't fermions be harder because of the having to
compute? Yeah, it is harder, but it has been done in the past. I mean, I mean, you're right. I mean, it will be. I think with scalars, it will be much. It will give a clear. I mean, a clear. I would say signal. I think this can be done. Yeah, but one should think. I mean, clearly what the issues. I mean, what the difficulties. I mean, what of this calculation would be. I mean, definitely open flux tubes with heavy quark sources. I mean, this has been done.
Right, but is that applicable to the J-dependent results that Simeon was talking about? That's a different setting, I think, right?
So it's hard to go to large J's also on the lattice as well. So I'm not sure that the exact comparison has been done, but Andreas, you might know what Lance was suggesting. So Sergey mentioned last week that Mike Tepper has done this in the early 2000s. It's one of the first calculations, and then you guys haven't followed up on that. But so if I understood it correctly, I haven't found the reference yet, but apparently in some of the early works, they've included also
This is something different. This is not. It's a different kind of operator. I mean, this doesn't have to do with open flux tubes, right?
Okay, all right. So
this is like more exotic, like an exotic.
Exotic, like particle.
Exotic,
okay.
Yeah. I mean, mesons with Y-shaped ejection. I mean, this kind of things. I mean, but yeah, I mean, this is definitely something that one should think about. I mean, what Lance suggested. I mean, yeah, maybe we discuss. I mean, later. I mean, whether to see whether this is possible. Yeah.
One short comment about this closed string lattice simulations. I mean, you guys are always comparing strings and lattice, but what about comparing it with experimental data? I mean, there are a bunch of flavorless hadrons. Probably most of them are mesons, but some of them may be also glue balls. And I think that it will be interesting challenge to see whether the results of the lattice simulations fit any of these experimental states.
Okay, I mean, I'd say that for the closed flux, there's no direct, I mean, the experimental data basically is the ones that lattice produce, because this is, I mean, your states, I mean, basically wind around the spatial direction. I mean, there is no something equivalent in nature, I mean, to compare your results with, I mean, regarding the closed flux tubes, right? However, for the open flux tubes, I mean, you can have hybrid potentials, and you can compare them to actual states. I think, I mean, I'm not aware of such comparisons, but I'm pretty sure that people have done that, and it can be done. Regarding closed flux tubes, I mean, yeah, I mean, basically the so-called collider is the lattice. I mean, is what we do. I mean, we collide phonons in some sense. Yeah, I mean,
just one very quick comment. There are also holographic models of confining strings, and some of that was done there too, right? Like where you put fundamental strings at the bottom of some warp throat and have them spinning.
Yeah, before I pass it over to Andrei, Simeon, maybe I don't think we need maybe you could stop sharing, then we can. I don't think there is a point.
So I have a simple question to Zohar, because you mentioned in the beginning of your talk that there are several notions of screening. And then you discussed condensed matter, and that's difficult for me to comment. But I thought that in field theory, there is only one phenomenon, which is called screening, and another confinement. For example, if you have a four-dimensional Young-Mills theory, and then you add one massive adjoint fermion and look at the spectrum of the theory, then the spectrum would involve the states with the mass around the mass of this heavy fermion, and that's screening. On the other hand, if you add a heavy fermion, which is with fundamental charge, then there are no states with the energy of order of quark mass. There are only states of order of 2 times quark mass, and that's confinement. So in field theory, I understand only one notion of screening. So can you probably comment more about what did you have in mind?
Yeah, I think I wasn't talking about condensed matter. I gave just examples from Wilson-Fisher fixed points, but everything I said is also valid in gauge theories. So if you have a gapped bulk, indeed you're right that basically there are 2 options, which is a perimeter law or an area law corresponding to constant or linear potential to first approximation, and there is nothing more to discuss. However, if the bulk is gapless, meaning just think about that there are power law correlators in the bulk. So if the bulk is gapless, then the notion of screening is actually very subtle. And even if there are fundamental quarks in the bulk, a fundamental Wilson line does not have to be fully screened. So what I mean by that is that when there are gapless, so the point of what I try to say is that when the bulk is gapless, there is a much more refined discussion of what screening means. Because in that case, obviously, all the interesting non-zero line operators will have perimeter law. Otherwise, we just call them zero and throw them away. But they're not all the same. They all have perimeter law, but there are sub-leading corrections to the perimeter law. So let me just put it this way to be simple. There is a perimeter law, which is the size of the loop, but then there is a constant piece in the expectation value of the square or in the expectation value of the circle. There is a constant piece, which is non-extensive. It's not linear in the size. And my point was that this constant piece is completely physical. It's renormalization scheme independent. And it allows you to distinguish what you mean by screening a little bit more precisely.
But this doesn't apply, as far as I understood, to Young-Mills theories with the heavy fermions. Well, because Young-Mills theory without fermions and with heavy fermions, they have gap, right?
Yeah. This discussion is only interesting for gapless models. And the point is that beyond the perimeter law, which we all know in lab, there is a constant piece. And this constant piece is universal, it's scheme independent. And like David Gross and Nadav Drucker computed it 20 years ago for the fundamental Wilson line in n equals 4 super Young-Mills. And that piece should be viewed as an order parameter for truly screened lines versus non-truly screened lines.
Zohar, do you think this would happen in QCD if massless quarks with massly
there are pions. If there are several flavors, there are pions, and that's
Yeah, if you are talking about a nonlinear sigma model, let's say in 3+1 dimensions, well, then the bulk is not truly conformal, but there is still a very interesting set of line operators, and then that discussion is actually even relevant for condensed matter physics. So yes, there is non-trivial physics in the pion phase. There are some line operators which appear in the pion phase that describe some impurities that are actually possible to even construct in the lab in condensed matter physics. We have a discussion of one particular such line operator in Appendix A from the paper from 3 weeks ago. So there are some logarithms on some line defect in that phase of the ordered phase. So yes, the answer, David, is roughly speaking yes. Even in the pion phase, there are interesting line operators with non-trivial defect entropy that you can compute, and it's actually observable even.
Sorry, Zohar, I'm confused by the language. I mean, if you look at the conformal theory, the potential between the quark and anti-quark is not constant. It's like a Coulomb. It's 1/L by dimensional analysis, essentially. So I'm not sure in what sense you call T/L perimeter law. I mean, David computed the coefficient of the 1/L potential.
That's
was
right.
a non-trivial function of lambda, right?
That's right.
It's not really perimeter.
The perimeter law originates not from the Coulomb potential. The perimeter law originates from the bare mass of this probe quark. Okay? And that's completely ambiguous. We don't try to compute it. It's completely ambiguous. You have to decide what is the bare mass of this probe quark.
Yeah.
For circular loops, what David computed becomes T/L is 1, and it's a physical observable. So I'm just saying, take a circular loop, then there is no ratio. There is no geometric ratio like T/L.
Okay, yeah.
You have a linear piece, which is the bare mass. This is garbage.
Yeah.
But then there is an object which you might call defect entropy, because in 1+1 dimensions, you can prove that this coefficient is exactly the thermal entropy of that impurity, the thermodynamic entropy of that impurity. And this you can call the defect entropy. And I'm just saying this is what you might think as a better characterization of which lines are actually truly screened. Because if this is non-zero, it's a non-trivial defect conformal field theory. So it's definitely not screened. Like this line would exist, it would affect bulk observables, and so on. So it's not.
Well, I mean, it wouldn't affect bulk observable. It would affect. I mean, it's a local object. I mean, how can it affect the bulk?
Yeah, it would, because there would be some power law decays of 1-point functions in the bulk. This is what people.
Oh yeah, if you're close. Yeah. I mean, if you're very close to the defect. Yeah.
Yeah, and so it's not completely screened, and it's observable in the lab. You know, the Kondo problem is exactly about that. So it's like it's an order parameter for what is screened that applies also in higher dimensions. It's basically a generalization of the Kondo G function.
Let me pass to Misha. He is waving, yeah. But you are muted, Misha.
Misha, you are not unmuted.
Misha, you have to unmute.
Okay, I have a quick question with regards to what was said by Zohar right now, that if you have a circular Wilson line, let's say, of course, there is no ratio of T to L because it's unity, roughly speaking. But then if you interpret the Wilson line as a dragging of a probe, very heavy probe quark, in fact, there is a correction to the bare mass of the probe quark, which is coming from dynamical gluons. You see, it's not that if you start physical, for instance, consider a really heavy quark, not infinitely heavy. And this has been done in heavy meson physics all the time. So the bare quark is being shifted by a quantity of order of lambda QCD or whatever your Mills theory, some dynamical scale, okay? So basically it's a soft parameter because the cloud around the probe quark is kind of large. Its probe quark would be like a point-like, and here, in fact, whatever you do, you have this. So of course, it's also adds to the perimeter law, right? It's nothing else than the perimeter law. Now, if you want a constant term, I don't know how to get it. I mean, what is this physical meaning? 1 over L term is clear what? It's Casimir term, right? What's the physical meaning of the constant? In the open string, it's clear what it is. It might be boundary effects, right? Because
no, but here it's not boundary, it's a bulk effect. You're asking about the physical meaning. This, first of all, it's a nice scheme-independent quantity. Secondly, it obeys some gradient formula. So it's a nice order parameter for RG flows between different impurities or different probe quarks.
Okay.
How to measure it experimentally is very difficult because you cannot make a circle in the lab. Unfortunately, time only runs forward and you cannot make it run backwards.
Yeah.
However, it does have a physical interpretation probably in terms of quantum information. So you can think about a vacuum with an impurity, compute some kind of entanglement entropy, and the result of that measurement might coincide with what I call defect entropy, but this wasn't shown yet.
You can add the Zohar and other impurity and have and measure the string tension. That's a measure of this whether the system is confining or screened. And as it is, as was done many years ago in 1+1 dimension, you compute the Hamiltonian of the system with with these impurities and subtract the ones out, and then you get a formula for the string tension in the one-dimensional case, but you can extend it also probably to higher dimensional cases. And it's I think a well-known result in 2 dimensions, but probably it can be also extended to higher dimensions.
Thanks.
Igor?
Yeah, maybe one can distinguish between a situation where there is perfect screening, where, say, the quark and anti-quark don't feel any potential at any distance, and the situation where at first it feels linear potential and then it levels off. I think
that wouldn't be a good enough criterion, unfortunately, because you can take 2 half BPS objects that have absolutely no force, but the BPS Wilson line is still a non-trivial defect conformal field theory. So unfortunately, that's not enough.
Well, can I ask a quick question about those Wilson loops? So most results are for the supersymmetric Wilson loops, not for this, right? That don't describe really an honest massive particle, but this 10-dimensional massless particle. What do you know about? What do we know in N = 4 about an honest circular Wilson loop or an honest rectangular Wilson loop?
Well, first of all, there's a nice paper by Polchinski and Sally from 2011 or so, maybe even before. Maybe it's 2008. I don't remember. in which they've established the existence of an RG flow from the non-BPS fundamental Wilson loop to the BPS fundamental Wilson loop of n equals 4 super Yang-Mills. They have done it in the planar limit at Wickett-Hooft coupling. So we have a lot of perturbative data about the non-supersymmetric Wilson loop defect.
So can you remind me, so from far away, if I'm far from the loop, it doesn't matter if it's not BPS, it looks BPS. Is that a statement, or if it, or it's the opposite, if I'm close?
No. When you're far away, there is always like some bunch of power laws, and the measurable quantities are the coefficients of power laws. And all those coefficients are different. These are completely different defect conformal field theories. It's just that there is an RG flow between them. Once you add the scalar, you integrate the scalar on the Wilson line, you trigger some RG flow towards the BPS Wilson line. Yeah, so there is this perturbative data at Wickett-Hooft coupling and large N. I don't think anybody studies finite N, but there should be perturbative data. I mean, it's not so, it's conceptually doable. We have now like several exact predictions in the large N limit and the large spin limit for some magnets, for some Wilson loops that I believe will be checkable in the laboratory soon. And there is, of course, the bootstrap, which applies to defect conformal field theory. And in principle, they should be able to produce some additional data.
Kavli?
Zohar, I trying to ask kind of about some rather old stuff, like particular what I have in mind is this old classical paper about the Schwinger model in 2D, where you have this kind of Higgs type of screening, right? When you start with, say, massless fermion. However, you kind of okay, for finite mass, still you have confinement, right? Of course, you know all this stuff, but I wonder, in terms of what we're talking about today, you know, how it fits.
How it fits? Well, let me just think for a second how to respond coherently. So 1 + 1 has a little bit of a special thing about it. I mostly wanted to talk about d bigger than 2, but 1 = 2 has a little bit of a special thing about it, which is that there are many examples of theories that are completely gapped, but Wilson lines are actually deconfined, as you know, like massless adjoint QCD, massless Schwinger model has deconfined fractional charges, this kind of thing. This is possible because these systems flow to two-dimensional topological field theories, and these lines become topological lines with S = 0. So there's something special and subtle about 2 dimensions, which maybe is not worth talking about now. However, that's exactly what Jaume talked about just a few hours ago.
Which that all gap models are deconfined.
Jaume told you essentially that all massless gauge theories in 2 dimensions are deconfined.
Yeah, but say,
which is I believe a completely correct fact.
Okay. Right,
well, the point is the string tension is proportional to the mass. So for the massless theory, it's a tension.
There is the phase of confinement as well, right? For non-zero mass.
Yes, Jaume told you that all massless gauge theories 2 dimensions are deconfined.
Yeah, I understand. Yeah.
Now there is a more refined issue of whether they're gapless and deconfined, they're gapped and deconfined, but okay, that's a higher order question. But they're all deconfined.
Even if you consider Schwinger model with massless quarks, which is deconfined, okay? Yeah. Okay, I agree with your statement. All of them are deconfined.
Yeah, this was shown by Coleman and Susskind, maybe. They showed that fractional charges are deconfined in the massless Schwinger model.
Yes, I agree.
All the masses are clearly deconfined, but there are also masses which are deconfined. because it depends also on the ratio between the charge of the Casimir of the dynamical quark and the external quarks. And it's very well known and all that.
Yeah, there are probably some deconfined massive theories as well.
Yeah.
Though I don't know of an example.
There are definitely examples of that in 3 dimensions, the confined massive theories.
You can add local topological operators to the action in 2D theories and drive the theory to confine or deconfine, whatever you want.
Yes. Yeah, there was a paper of Alexei showing this a few months ago.
Hey, Zohar, we had a question the other day about what's the maximal supersymmetry in 4 dimensions that exhibits confinement. Is n equals 2, pure n equals 2 confined?
I'm just thinking how to...
4 dimensions?
Yeah, 4 dimensions.
It confines.
No.
Why not?
Well, it's gapless. I don't know. Let me just think. I have to think about it. It's gapless but confines.
It's Coulomb, I thought.
Yeah, it's gapless and confining.
So what are the gapless states?
Is it really confined? I'm just deliberating. Are there actually Wilson lines for which it confines? I don't think so. Actually, I don't think so, Jaume.
Well, there's nothing in the fundamental. Can you
Yeah.
But in Cyberg-Witten, you needed to break to n equal 1 to see the
for n equals 1, of course, once you leave the Coulomb branch, it confines. But with just n equals 2 supersymmetry, I don't know if there is a confining model. But Offer is the right person to ask. Maybe Offer is in the audience.
Yeah,
I also don't know any confining model with n equals 2.
Yeah.
Because the Cyberg-Witten paper says confinement. It doesn't say break to n equals 1. So there's something subtle there going on.
That's what they do inside. That is what they do inside the paper. They do break to n equals 1.
They do break to n equals 1 inside?
Yeah, they break to n equals 1.
Yeah, they see some singularity, and then to resolve it, they break to n equal 1.
There is a massless photon.
And then they have these monopoles.
There is a massless photon. I do not believe that there is a Wilson line that would not couple to this massless photon.
So that's what you would need to show confinement, is to
Could
have
be,
a Wilson line.
look, as a matter of principle, just theoretically speaking, there could exist a defect in that theory, which just doesn't couple to the massless photon and has area alone, and also charged under the one-form symmetry. But I don't know if such thing exists. Most likely it doesn't.
Excuse me, if you have n equal 2, without breaking n equal 2, you can, if the gauge group has a U1 factor, you can introduce the Fayet-Leopoulos term, right? Which also lifts the flat direction, right? So it may be still, it may be without, Is it confining? I forgot, or is it?
The Fayet-Leopoulos term would not couple to the low energy photon, if I understand correctly, Misha, because you just have U1. You had the Fayet-Leopoulos term.
No, it's not. Fayet-Leopoulos term can be added to U1 factor only. It cannot be added to the gauge, non-abelian gauge field.
No, but just think about the low energy. Think about the low energy limit. It's one U1 vector multiplet. If you had the Fayet-Leopoulos term, it doesn't lift the Coulomb branch.
Okay.
Because the scalar field is not charged under the U1.
Yes.
So I don't think you can lift the Coulomb branch in this way.
Yeah, it's not. It doesn't make the. For neutral scalars, yes, you are right. Still, they're still flat. I mean, they belong to a flat direction. Yes.
All right. Thanks.
Is there any other question, comment? If not, let's continue physically in the afternoon. And let's thank everyone for a nice morning, and in particular
Great discussion.
Simeon
Thank you.
and Zohar.